We get a lot of questions about how muscle oxygen information can be used to prevent injuries, and one of the examples we often give is with runners when they're doing interval training, that we can use muscle oxygen to help them know when to stop their intervals so that their technique can be maintained. Can you talk about that example?
That's a fascinating topic, and I use that daily in my therapy with people in rehabilitation. Again, in the past, I used the clock and say you do 20 or whatever. No physiological reason. I would say based on experience.
Okay.
And potentially based, if you had time to watch your client, you could see he started to fall apart. The way he made the exercise, you would have to tell him, oh, you have to stop, you need a break. When you give a home program, and I use that stupid word cookbook, then he may push the 20, but really the meal would be better if he would have stopped cooking by 10.
Okay.
No. So when we now use that particular example, if in classical track and field, we do intervals based on distance and on time. So we will tell somebody, if I don't have a 400 meter track, go 30 seconds or go 400 meter. And I'm not always very nice with coaches, but I say it's more an organizational reason than a physiological reasoning why I do this. I mean, the 400 meter are very nice for me as a coach because I can stop and start on the same place, and the athlete has to run around, start with me and stop with me. Whether that's a good distance, we're not going to argue because it's a discipline. But do I really have to run 400 meter to get better in a 400 meter? And potentially it's important that I can run 400 meter, otherwise I never enter the race.
Right.
But the training, I mostly don't run one all out. I may run 10 times 400 meter. So I may not even run the speed needed to actually have a good 400 meter. So the question is, there more quality of training than quantity of training? And a part of the quality of training is avoiding injuries. So when I now do a 400 meter interval workout, I have certain muscles, they are really given to run perfectly efficient. So I just use one simple one. Your hip extensor, your gluteus maximus, is one who helps you to really fly, look nice in the air. So that guy is the guy who really starts from the beginning, when I technically run properly, to work very, very hard. So I have to assume that he is the guy who gets most loaded and has potentially the highest risk. That is the first guy who complains that it's getting a little bit tough towards the end. So when I force an athlete to keep running 400 meters, but his main guy, his main worker, can't sustain the performance, he still has to finish that run. So luckily for us, we have the boss who is doing a perfect job, and he has a few apprentices who help him to try to make a perfect job. The apprentices are not perfect. They are close to perfect, but not perfect. So we have muscles in our hip area who still can help to extend the hip, but they have some small disadvantages for that particular movement, that they may turn the hip a little bit out, so-called outside rotation or external rotation. So when I force my body to run, these guys are not completely fatigued yet because they didn't work from the beginning that hard.
Okay.
And as your brain says you have to finish, the main boss says, well, I showed you how to go 300 meters, now you have to help me. And the athlete will change technique. And everybody who looks at 400 meter run sees that. You know, from an incredible flying, nice technique, you can see they start fighting. They tense up, their legs go differently, they lean more back, they start to rotate out. So you start to make not anymore a perfect line movement for that particular discipline, and you start to rotate. So when you assume now your foot makes this external rotation movement because that muscle helps you to move forward, and you put some spikes in your shoes, you can imagine how that rotation goes. So it's a rotation who will go on your mechanic. And one of your mechanic is your ligaments and your tendons. And one of the guys who potentially doesn't like that too much can be your Achilles tendon.
Okay, so how can NIRS be used to identify when that happens?
So you can actually see it. I mean, if you have your NIRS on the main worker and you see the guy runs out of money, he can't spend anymore, so you see SMO2 drops dramatically fast. You whistle as a coach and you stop the load. So it may be by 322 meters, no? And he rolls out, and he trained 322 meters the optimal technique and started to stop the risk of a wrong mechanical load.
Okay.
No. This is a very important part. There is some additional parts in there. In the moment where SMO2 in the main muscle gets very low, that's where the connection comes to lactate. He starts to create oxygen-independent energy. And a part of this oxygen-independent energy is hydrogen ions or an acidic situation. That means you create a metabolic acidosis. And there's beautiful research out to shows that when you create a metabolic acidosis, you have a much higher risk to deplete calcium. which then can lead to, in track and field, very common stress fracture. So you have a mechanical force who creates a mechanical strain on your lower leg area, on your shin, on your Achilles tendon, with inflammatory reactions, and you repeat it over and over again. You get a fatigue of the equipment, of the material, and that's very often we see a sign of injury, and then certainly shows up as a stress fracture.
Okay.
So again, when I stop him, when I see SMO2 doesn't drop nicely anymore, I have a much smaller risk to create this metabolic acidosis.